Good morning, class. In continuation of the topic we started last week, which is electrochemistry, we will round it up with the last component of it. The first component was electrolysis, where we discussed the, the electrolytic reaction in this particular type of cell. The second component of the electrochemistry topic that we are looking at is the electrochemical cell, which we concluded yesterday. The third component of it is to discuss cells and batteries. Cells and batteries. Okay. Before we go on to that, I would like to quickly draw our attention Sorry about that. Before we go on, I'd like to draw our attention to, because every day after the lecture, I always try to go back to the video, to watch, and I realized that there is a misinformation, which I think it is important that we correct it. As my head was thinking about delta G equals minus RT link K, my hand was writing a different equation on the solution to Fe2 plus / gold 3 / gold problem. Okay, but what surprised me more is that nobody called my attention to that, showing that you were not following. Okay, so delta G equals minus RT link K is the equation, not what I wrote as delta G equals 0.059 over N log K. Okay, not what I wrote. This was meant to be E, not G. All right, so I haven't found your E cell to be 1.960 volts. Okay, the appropriate equation is to then determine your delta G from minus NFE, okay, which we discussed yesterday. When you determine your delta G from here, you can bring your delta G to this place and then determine your K. Determine your K from here. All right. So that is supposed to be the correct thing. All right. Here we do not only train to learn, we also train you to be courageous, to speak when you see something that is wrong. Okay. I expected that one of you should have, mentioned it yesterday. And that is just to, clarify. And we can go on to today's uh, class, today's lecture. All right. So for today, we are discussing cells and batteries. What exactly is the difference between a cell and a battery? Okay. A cell is a single unit of device that converts chemical energy into electrical energy. Daniel cell is an example. Okay. It converts chemical energy into electrical energy. Chemical energy, the use of chemical materials to produce electrical energy. You realize that in this particular type of cells, we always talk about the EMF that the cell will produce. Because once the cell can produce a voltage, current, electricity will flow through the external circuit. All right. So a battery, in the same vein, is a collection of cells that convert chemical energy into electrical energy. The difference between a cell and a battery is that a cell is a single unit of device, a single unit. Okay, you have this unit, and when they are put together, all right, depending on the composition, they can make a battery. Okay, while a battery is a collection of cells, collection of single units of cells that convert chemical energy into electrical energy. The actual definition of a battery is not only, that it constitutes a collection of cells. Another important definition is that batteries are reversible. Okay, the electrode reactions that occur in batteries are reversible, which is not what you find in cells, which means batteries are often referred to as secondary cells because they store energy. They store energy, they discharge the energy, and they can be recharged. They discharge in the forward reaction and they can recharge. You have recharge backward, discharge forward, okay, for batteries. Discharge in this direction, in the forward direction, recharge in the backward direction. And they are made of multiple cells. Batteries are made of multiple cells. Okay, the Daniel cell had been discussed. We have discussed the Daniel cell. There are some other chemical cells which, like the Daniel cell, have been used in the past to generate electric current. Some of them have been used in the past and some are still being used now. So examples are the standard Western cell, okay, the Leclanché wet cell. Okay, we have the Leclanché wet cell and we also have the Leclanché dry cell. There are different types of the Leclanché dry cell. We have the one that we use ammonium chloride as the electrolyte and zinc as the anode to use zinc as the anode. One thing that is common to this Leclanché shell is the cathode. The cathode is the material that the cathode is made up of is usually the carbon plate, and around that carbon plate you have manganese 4 oxide with powdered carbon. That is the common cathode for this Leclanché dry cell, and in fact even the wet Leclanché cell. So different types of dry Leclanché cell, I want you to note this, includes one, the ammonium chloride zinc dry cell, where you have the ammonium chloride as the gel, as a gel, and the zinc, which is going to be one of the electrodes, in fact the anode, okay, and the general cathode generally for this type of cell is made up of carbon plate surrounded by powder carbon and manganese 4 oxide. Okay, that is the common cathode for all of them. Okay, even the wet Leclanché cell, the common cathode is manganese 4 oxide with powdered carbon. So you also have alkaline, in this case KOH or sodium hydroxide will be the electrolyte, while zinc will still be the anode. Okay, and we also have magnesium ammonium chloride or alkaline dry cell. In magnesium, instead of zinc as the anode, we have magnesium there, no zinc. So the electrolyte can either be ammonium chloride or sodium hydroxide or potassium hydroxide. When we say alkaline, we mean potassium hydroxide or sodium hydroxide. So another example of cell is the fuel cell. So let us look at the Leclanché wet and dry cell together. The wet, okay, there could be spillage because the electrolyte, which you can see here, is ammonium chloride solution, aqueous ammonium chloride solution prepared with water. Ammonium chloride salt dissolved in water is the electrolyte. You have the zinc rod, which is here. The zinc rod is the anode, and you have the carbon plate. This is the carbon plate, all right, which is your cathode, and surrounded by powdered carbon and manganese 4 oxide. The manganese 4 oxide is a depolarizer because around this place you could have hydrogen, which is not going to make the cell, operate with high efficiency. So the manganese 4 oxide helps to convert the hydrogen gas around the cathode to water. Okay, and you have what you call a porous pot, which houses the carbon. This is to control the rate, okay, the rate at which the electrolyte gets to the cathode, okay, to provide the controlled rate at which the electrolyte gets to the cathode. Everything is what? Contained in a glass jar. All of this is contained in a glass jar. Okay. The type of reaction, this particular type of cell can produce a voltage ranging between 1.6 to 1.4 volts. Okay, and it is not stable, it is not constant due to polarization. The polarization is the development of insulating barrier between the anode and the electrolyte during production of current. So when current is being drawn from the cell, you produce some material. One of such materials could be ammonia gas being produced, okay, and this ammonia gas can stick on the surface of the cathode, thus reduce the efficiency of the cell. Okay, and the ammonia in the presence of zinc ion can turn to a crystal, what we call zinc diamine. Okay, this crystal can clog on the zinc rod, thus the cell from an optimal efficiency. See the electrode reactions using the Leclanché dry cell example. The Leclanché dry cell and that of wet cell is almost the same thing. They upweigh. The only difference is that the wet cell, the ammonium solution is used, while in the dry cell, gel. If you the common Tiger battery that we use, some wall clock or timer, that is an example of a used till today. It can produce a voltage of 1.5 volts. It looks like what I'm holding. The Tiger battery, for familiar, you remember this is still being used, and like the one I'm holding, it is a battery. The actual, to say, a cell. Okay, you have the carbon plate, okay, surrounded by powdered carbon dioxide, just as we have in the. Then you have the zinc can is the coating, is the in the battery. The metal plate around the battery is okay, and what you see is what you call insulating cover, insulating, and inside of it you have carbon plate, all right, carbon plate, and then you have a brass. The top here is brass, okay, and then you have this insulating Tiger battery. What you have top plastic seal, looks like blue in color, okay, blue in color. That is the top seal for the in particular. Okay, have the ammonium chloride gel in blue here. Ammonium chloride gel by ammonium chloride salt with to produce the gel. And the reason to avoid spillage, okay, over the wet Leclanché cell is not, we are still using the dry today. Okay, if you break that, the cardboard disc inside it, all right, the card is also to provide to separate the ammonium chloride from powdered carbon oxide, okay, the can, all right, using negative contact through at the back of the. You have the pole, which is made up of, surrounded by depolarizing mixture of powder oxide in a porous in the sense that control rate at cathode. So the manganese forms as the cathode, okay, on an inert, okay, it serves to oxidize any hydrogen present to water. Okay, I've said that the pot and the negative electrode are placed jar containing a solution of, okay. So the component of the wet plant cell is the same as that of the, and I've told you that is that the electrolyte in the wet, while for the dry plant the electrolyte is ammonium chloride gel. The dry cell is now used of the wet Leclanché cell. The dry Leclanché cell is made of the same component as the wet Leclanché cell, except that ammonium gelled by the addition of, instead of aqueous ammonia, to prevent spillage. Okay, the dry cell is used in flashlights, portable radios, timers, televisions, wall clock, sound system, monitors, and so on. So now, when we consider the actions in the dry cell, at the same time considering the electro reaction in the wet cell, because are governing chemical reaction. So on the anode, which is where the electrochemical reaction begins, you see the zinc rod, okay, producing zinc 2 and 2 electrons, or 2 electrons. That is what we shade the electrochemical process. And on the cathode, the manganese, okay, takes up some of the water it haven't, oxygen around it to water. And so takes up some and also take up the coming from the anode, to give you manganese 3, manganese 3 and hydroxide, in the presence of zinc ion to produce zinc hydroxide cell reaction. So uh the cell EMF, E cathode, E cathode, E anode. Cathode is 0.74, E anode is minus 0.76. As you know, for this electrode, is 0.76. So at the end of plus 1.5 volt. So the cell can produce a voltage of 1.5 volt. Not all the hydroxide ion to, which is a solid material, and at the same time, ammonium chloride can undergo hydrolysis. Ion in ammonium chloride undergo hydrolysis, that is with water, can react with water to produce ammonium hydroxide and hydrogen ion. So this medium is an acidic medium. I want you to note that is an acidic medium, is H plus. Writing is a bit so hydrogen ion H plus. Ammonium hydroxide plus H plus. All right. That is, this reaction is intrinsic. It is intrinsic. You have it at the background. So the excess hydroxide, I want you to note that this will always be available. That the environment is acidic. Accelerate the rate at which zinc dissolves in the electrolyte. The zinc ion dissolution into the electrolyte is going to be accelerated because that environment is slightly acidic. It's acidic because of the formation of hydrogen ion. Meanwhile, not all the hydroxide ion will be more. Not all the hydrogen react with zinc from here. You produce all the hydroxide ion will react with the zinc to form zinc solid hydroxide, which we have here. So the remaining hydroxide ion will be mopped up by ammonium ions from ammonium chloride to library. So this is another very important reaction. Ammonia is used in the process. When ammonia is produced in the process, this ammonia is reduce the efficiency. It will reduce the cell because it's a polarizer which can clog, cling of the cathode, thereby preventing cathode from performing efficiently. So the ammonia from action between ammonium ion, which is from and hydrogen ion, which is the cathode, produce cathode. All right. So mopping up with this ammonia, which is a material that is good for the cell. So the ammonia gas falls to the cathode and cause the disruption of the. The ammonia gas formed can adhere to the cathode, the disruption of the current. This is formation of a complex ion. Complex ion crystallize as a white salt. So for some of you who are familiar with Tiger battery, after a prolonged use of the Tiger battery, you find at the negative plate the cell some white crystal, and that white crystal zinc diamine is zinc diamine chloride. The zinc ion can take up the ammonia in the ion. As you know, ammonium chloride is the source of the chloride ion, to produce this white crystal.